Okay, so today we're going to look at our tests for convergence or divergence. And there's two different types that you can do for when you're looking at improper integrals. The one in yellow is the one that's like most used lately, but you can also do the limit comparison test, and we end up doing a limit comparison test when we get to explore convergence and divergence with series. So since LCT comes up later, it's always good to kind of get your feet wet and take a look at it now. So the first one, let f and g be continuous on the closed interval from a to infinity, where 0 is less than or equal to f of x, less than or equal to g of x, for all x is greater than or equal to a. So I'm going to just pause right there. This should look familiar to what you guys were doing with the sandwich theorem. Okay, so kind of tying into older things. So you're taking a comparison between two different functions, and 0, which y equals 0 can be considered another function. So kind of sandwiching it in there to kind of understand what's going on. But there's two different ways to kind of look at it. So if you have the integral of f of x with respect to x from a to infinity, so this is improper integrals. And that's why we're looking at doing these tests, because when we're looking at the other lessons, there were some times where your integral converged, you got an answer for it, and then other times it was diverging and you weren't getting an answer. So if you happen to know whether it converges or diverges, it kind of gives you a heads up as to whether you're going to continue to evaluate and get a number, or you just say that there's no value or no solution. Okay, so in this particular case, number 1, if that improper integral for f of x converges, then the integral of g of x with respect to x converges also, as long as it's from that same upper and lower limits of integration, a and infinity. Now, 2 is the integral of g of x with respect to x from a to infinity. If that will diverge if you find out the one that you're working with, f of x, diverges. Okay, so hopefully you had a chance to write that down. Now I'm going to read the limit comparison test. So if f of x and g of x are two continuous functions, for x is greater than or equal to a, so same sort of understanding, f and g need to be continuous, okay, on that closed interval, except when it goes towards infinity. So f of x, if it's greater than 0 and g of x is greater than 0, and the limit of f over g as x approaches infinity is found, okay, that's actually L, and L is between 0 and infinity, then either both of these converge or both of these diverge. Okay, so it's either going to work out nicely that you're going to get an answer because they both converge, or neither one of them is going to work out and it diverges. You're not going to get an answer. So let's actually take a look at doing these tests so it'll make more sense to you. Let's pull up some examples. Here we go. Okay, so since the last thing that I had done was talk about LCT, I'm going to actually do number 2 first, and hopefully that makes sense, how we're going to use that to show that the following converge, and then in number 1 we'll see by using DCT if it converges or diverges. So here we go. Alright, so A, let's take a look at that. So we have the integral of dx over 1 plus x squared from 1 to infinity, and we're going to show that it converges by comparing it to a different function. So if you were to look at the degree in the denominator, or the function that we have there, 1 plus x squared, we would focus on, let's say, n behavior model and take a look and say that's really x squared. So if this is 1 over 1 plus x squared, what I would do is compare it with 1 over x squared. And that's a good function to be working with, because if you were to graph 1 over x squared and 1 over 1 plus x squared, you would see that they are positive and continuous on 1 to infinity, okay, which is my lower and upper limit of integration. So let's take a look at our function here. So we have this given to us, and we're going to analyze looking at the limit of 1 over x squared. Okay, that's my f of x with 1 over 1 plus x squared. This is going to be as x approaches infinity. So if you were to do keep, change, flip, then we have 1 plus x squared over x squared as x approaches infinity. This is an infinite discontinuity. And if you look at our rational function here, we know that there's a horizontal asymptote at y equals 1. So the answer here is 1. Okay? And you could also use L'Hopital's rule. Okay, and you get 2x over 2x, and the limit of that as x approaches infinity is 1. So we are getting an answer of 1 here, which means it does converge. Okay. Now, what it actually converges to may not be 1, but that's for you to evaluate. Okay. And we went through the different ways to evaluate that. So this does converge. Let's take a look at B. Okay, so in B, we're going to do something similar. So we're going to take a look at using 1 over, not like -5, but e to the x. Okay, and so I'm going to take the limit of 1 over e to the x and divide that by 1 over e to the x minus 5. So again, it's very similar for us like doing a behavior model. And if we do keep, change, flip, okay, this works out nicely so that each term is divisible by e to the x. And that's something that you may want. So if, let's say, you're not sure what should be your bottom function or top function, it's something that you want to be able to find your infinite limit. Okay, so like I said, we have the limit of 1 minus 5 over e to the x, and as x approaches infinity, so imagine that it's e to the infinite power, which would mean that it's infinity. 5 over infinity, or 5 over a very, very large number, is going to become 1. So the limit of 1 as x approaches infinity is just 1. So once again, we found out that this converges. It has to come to an answer. It worked out that these answers were 1. That doesn't mean that this will evaluate to 1. So do be careful of that. Okay, so you just saw the limit comparison test. Now we're going to do our other test, which is going to be our direct comparison test. And hopefully we see something here that diverges, because so far everything's been converging. So let's take a look at 1a. So we need a function that will work so that we can compare with the our function that is our integrand. So you have to think of that as a function, okay? And so okay, our integrands are our functions. we're going to compare it between 0, which is our x-axis. Sorry, that turned out a little sloppy. That's a 2 here. And 1 over x squared. Okay, so if you were to graph it on this interval, okay, from 1 to infinity, okay, they do intersect, and you do notice how the sine squared of x over x squared is, it has y values that are smaller than 1 over x. This is something you would want to check with your graphing calculator to make sure that this so far is true. And then we proceed to take a look at what this is. So if you were to find the integral of 1 over x squared with respect to x from 1 to infinity, and you find an answer, that would be great. Well, we did have an answer. This was in the other day's lesson. Okay, so I believe it was 2 lessons ago. Actually, it could have just been in the last lesson, so I apologize. So this was evaluated as 1 over p minus 1. Okay, so this does converge and it does have an answer, which is important. Okay, so we can figure out what this would be between. So it's 0 is less than or equal to some value, which is less than or equal to, all right, so p minus 1 has to be where p is greater than, by the way, p has to be greater than 1 here. And in this case, since our exponent is 2, then p has to be 3. Okay, so this is at the end of our last lesson. If you didn't see that portion of video, do check it out so you can understand where this formula is coming from. So our final answer would be 1 over 3 minus 1. We can all do 3 minus 1. So that's 1 over a half. So we end up with the following answer. And so since we have something that we can work with here, it does converge. Okay, so we can say that A converges, okay, and that's because we know that this will converge as well, and voila. Okay, so now we're on our last problem, and we're taking a look at this particular one, whether it diverges or converges. So for this particular problem, let's just kind of narrow it down to you got 1 over the square root of x squared. Doesn't matter if we're like subtracting 1 or 0.1. And this is very much like 1 over x. Well, we know what happens with 1 over x. I think that was the one we did like 2 lessons ago. So we found out that this diverges, okay? And I think we even saw it in the last lesson where we got that formula for where p is greater than 1. Well, that's when it converges. You can use that formula. When p is equal to 1 or less than that, then it's going to diverge. And so you can compare, and it is a comparison, these two functions. Okay, and if this diverges, okay, in this case this is 1. If this diverges, which we found that it does diverge, then this does as well. Okay, so this one does diverge. So at least one of these 4 problems diverges. And that's great. So you got to see how both tests work, how some prior knowledge kind of came in there, and that you can get different answers. Okay, so check them out. Good luck, and let me know if you have any questions.